Hi,
Seconds.
I think we are online. Am I correct?
Yes.
So, hello everyone, and welcome to the CMS control room, which you are already hearing, but we will explain this later.
Yep.
First, we will start by introducing ourselves.
So, hello, I'm Derek Grove. I'm a PhD student living here in Geneva, Switzerland, although right now we're in Cessy, France, to work on the CMS experiment. Um, and I'm happy to show you the experiment today.
Fair enough. Hi everyone, I'm the second guide. I will stay here, so upstairs, with respect to the experiment. I'm Giulia, I'm from Italy, Milan, and I am as well a PhD student in the CMS experiment. And actually here together with us, there is a huge team. There's Zoltan and Noemi, the technical team for the visits, and Rona and Sofia. Oh, they're appearing. Here's everyone, Rona and Sofia from the communication team of CMS. And we are all here to welcome you and greet you, and we're happy you're joining our visit. And feel free to ask questions. We already have some that have been asked on Instagram, so we will be answering this throughout the call. So I guess we can start. Explain what we have around us.
Yeah, we can go around the control room, right?
Yes, definitely. Can we have a trip? So now I will explain to you, first of all, where we are. So you should be able to see a map. Right now we are in CMS. You can see it on the very far left of the picture. It is one of the 4 biggest experiments that are on the LHC ring, so on the Large Hadron Collider, which is the particle accelerator we work in. We are right now, as I said, in CMS, which is underground. We are about 100 meters below ground in France. Right now, we are actually, well, still on the surface, but Derek will bring you downstairs. And you can see that our cavern is the one down here on the bottom, and it's the lowest we have. We're actually the deeper experiment.
I did not know that, but it is, I knew it was tilted.
Yes, yeah, exactly. The LHC is tilted, and this is done to place it on the on a, let's say a ground that's solid enough, I think, to sustain us.
The term I heard is a granite slab.
Oh yeah, fair enough. Yeah, that's
They
fair enough.
wanted, yeah, when they were constructing the LHC, they wanted to, it's a massive engineering project. They wanted to make sure it would be as stable as possible, so it wouldn't tilt over time. And I believe that's why they dug so deep and
Yeah,
built
exactly.
it on this.
Well, this gives you a bit of an idea of how complex of an engineering effort this is. So it's not only about the physics of it. And well, also you need to imagine that like also for the previous experiment that was in here, we were sensitive to like the high-speed trains that were
Oh, really?
passing. Yeah. We could see like the vibration. There was a like it was seen in the detector. So it's really a very precise experiment that we're running here. And I guess we can walk you guys around the control room. Yes, we can. Can we ask for? Thank you very much. So there we are. This is the surface control room, which is where we have all the PCs that control and monitor the experiment that's running underground. As you see, there's a lot of monitors. Here we are. Hi, you guys. Now I think Derek and Noemi will walk you through all the spots, and we. Okay, Noemi will walk you through the spots, and we will explain what they are a bit. So, okay, you go first. This is the technical spot.
Okay, the technical shifter. So I know the shifter mainly as the person that owns in quotes all of the various subsystems of CMS. So for example, the pixels, the innermost layer, when we want to do something involving the high voltage, we need to get permission from this shifter for us to take control and do the sorts of things that we want to do with the high voltage. So this shifter is very important for having this kind of ownership over various sub-detectors and making sure nobody's trying to do too much at one time. A bit to the right, you see all these camera feeds. There are cameras all throughout the underground. So when we're down there touring, I'll actually be appearing on these cameras. We take safety very seriously here at CMS, so we want to monitor the underground 24/7.
because, well, we can't be downstairs, inside the experimental area when the beam is on. So the cameras help us ensure that no one's there. There's a lot of different safety systems, so they're redundant, but we have also this, let's say, very practical, very easy one. You see someone, if yes, that's a problem.
Yes.
So this shifter is the safety one also. It's like quite important one.
And the
Ooh, that's a screen. That's a beam screen. That's actually one of the important things that we have. This is actually accessible on the web by any of you guys as well. We are able to see through this what's the status, for example, of the physics beam. Here you see proton physics stable beams. This means that we are actually right now live in the data taking. So that's the screen that we use to know the situation of our detector.
Right. The screen here shows actually the status of the whole LHC. So, for example, we're one experiment of 4 main experiments. So this screen shows you the current stats of the LHC. It's important to us to keep track of what's going on with the beam.
Pretty much like if they call you during the night because there's a problem and we are taking data, then you need to really get scared and get your stuff moving. I can take the chance to answer to a question that I saw appearing live. Someone asked if we get to choose the experiment we work on or if we get assigned by it random. So, okay, you're with a US university, I'm with an Italian one. So it might be a bit different by country, but for example, in Italy, you pretty much get to choose in principle because you, let's say, pick the PhD project based maybe a bit on which experiment is available, let's say, in your uni. For example, in mine, we have CMS and LHCb. We do not have, for example, Atlas. So staying in that uni, I could have not joined the Atlas experiment. But beside that, you get to choose. And you also need to know that we have, let's say, 2 experiments that are more general purpose, which is CMS and Atlas. They were built with the specific objective, let's say, to see the Higgs boson, while the other 2 are more generic ones. So now we are also showing you a picture. You see Atlas, which is the top left, and CMS top right. Those are the general purpose. I remind you, we're in CMS. While the bottom ones are more specific. So we have Alice, which does heavy ion physics.
As far as I know, yeah.
And the LHCb that does B physics, so a sector, let's say a sector of the standard model that is very specific. So based on what you prefer, I guess you can choose. For example, I was interested in the project that we were doing in CMS.
Yes.
I guess for you it was similar, right?
At least for the US institutions, it's probably very similar, but the university you go to for your PhD program or master's maybe, they'll usually have a group working on one of these experiments, and then you're kind of locked into that experiment.
Yeah, definitely. Once you're in, you're in.
Yes.
At least for the PhD.
Yes. So my university, University of Kansas, we only have a CMS group. So we're all CMS scientists. If you wanted to work on a different experiment, you'd look for a different university, I suppose. But we're all one CERN. That's not a saying, but we still feel a sense of community, and we're all working for the same purpose, even though we're on different experiments. So.
Yeah, that's true. We keep showing you the control room. Please feel super free to write us questions if you want. Oh, we're the big stuff, the shift leader.
Yes. Well, the shift leader is in charge of making sure all the shifters here in the room are, I would say, doing their job, but they're always doing their job. Superb. But they also communicate with all of the other subsystems. So it's usually if you're on call, there's other shifters that are not in the room during the day, but at home, but they're on call. The shift leader is the one that will usually call them to report an issue or ask some questions. The beam has dumped. Would you like to do this? So they really are in charge of making sure all of the shifters are working together in sync and all the subsystems are operational. It's a very important job. Seems stressful.
Yeah, pretty much. Also, you get to call people during the night. So yeah, it's a hard task, but that's fine. Of course, well, we're taking data 24 hours a day. So that's why I talk about getting cold during the night. We, of course, don't want to waste the data that the LHC is providing us. So when basically we start running, we start and we go on for about, usually, if everything goes well, 12, 13 hours straight. And then straight afterward, we get another field of protons. So we have new set of collisions. So we're running 24/7 for about 9, 10 months a year. During winter, December and January, February, we usually switch off everything because the electricity needed to run the LHC is a lot, and sustaining the running of the LHC together with the winter requests of electricity by Geneva and the other towns here is not as easy. So we prefer to shut down in winter for the operations. We go on with the DRQ. You see the next step, let's say, which Noemi is showing us is the DRQ, which stands for data acquisition. So basically, this is a shifter that checks that all the systems, all the parts of CMS are sending data correctly. So nothing is, let's say, stopping everything or crashing the run. This is quite a big responsibility as well, because you need to take care of a lot of different, let's say, variation and to pick the correct, let's say, setups and configuration for everyone. So this is one of the, let's say, complex shifts. I see I see her shifter looking at us, very happy. So yeah, it's a hard one. We go on. Trigger is the one I probably know the least. So I'll let you talk about it if you know some more.
Once upon a time, I was trigger shifter, so
Then,
I should know
perfect. I'm the
a lot about it. Yeah, so trigger is actually a very important, we would call it a subsystem, I suppose, of CMS. It's a very important component, maybe. And trigger usually, we use it to filter the events that we record from the collision data. So trigger here, the shifter, is responsible for making sure we have the proper, I believe it's called trigger recipe loaded. But the way I think that's the proper term. I could be wrong, but the idea is, what percentage of what unique events are we going to record from our collision data? And they have to make sure that we are constantly recording the correct events, basically, with this certain recipe.
I would maybe take some seconds to answer to some of the questions. I think this is a set of questions that were asked on Instagram. So maybe now that we're still upstairs, it's a good time. Tell me if you want to pick one of them. I will read them first. So a question is, in our experience, what's the most surprising result that we have observed in the detector? Well, okay, let's say that it was not actually a surprise. It was hoped for, but I would say it was the Higgs boson. At least this is for the CMS experiment, because the idea was that we never observed before the Higgs boson, but it had been theorized up to about like 50 years before it was actually seen for the first time. So it was 50 years of, let's say, from when the theory was built to when we thought how to build a detector that could see it. We actually started the project, started the funding, started building it, and finally running it. So this is in some sense surprising because it was a huge effort, but we dearly hoped for it, let's say.
And we did
I don't know if you have any, I don't know if you have, oh, that was it was 2012, by the way.
A while ago, yeah. I mean, it's a bit of a hard question because the way we do the data analysis, it's a lot of statistics. So although it's very cool to look at one event, which I believe you're asking about, we actually have to look at thousands, millions, billions, trillions of events at times. And so it's a bit, it's hard to say there's a particular event that stuck out, but the Higgs boson is, the reason the Higgs boson is very exciting to us particle physicists is it has properties that none of the other particles in the standard model have. And this would be spin zero, the technical term. but we produce this particle here at the LHC inside CMS, and it's the only place in the world that we can produce it and study how it behaves. So to this day, it still remains the most, I think, exciting thing going on inside CMS that we're studying.
Okay, we have a lot of questions, a bit more on our career path. We can pick them up later because I see one that's a bit more, let's say, related to what we're talking about right now, which is that's a hard one. I will pass it to you. If you could redesign CMS system from scratch, but keeping constraints that we have right now, what would you change? Okay, if you have an idea, you go.
I mean, my changes, they'd be very selfish because there's the things I'm interested in. I would love, and you know, the technology may not be there. We've developed better technology. We're about to upgrade CMS with this technology. So if I could rebuild it now, we have these better pixel sensors, much smaller, higher resolution. And if we had an infinite budget, I would do a lot in a lot of these pixels more
That's
than
fair
we can to get higher resolution closer to the collision point of our charged particles.
That's fair enough.
Yeah.
Actually, I have a comment.
Okay, Zoltan's jumping in.
We don't redesign from scratch,
but we are about
to change many things in
That's
the CMS
actually
experiment. That's going to happen within half a year. We are going to
Yeah.
enter in the a bit more than half a year. We are going to enter the so-called long shutdown 3, where we are going to redesign many things, rebuild many things, a completely new detector part, the so-called high granularity colorimeter will get in, that will change many things in the future. Also, we are going to install new detectors in the muon system, jam chambers.
the MTD.
The MTD as well. So quite a few of the things are going to change. And that's also true for the detector. This is an experiment, and please understand the word or taste the word experiment. We are always changing. We are always trying to catch up with the needs.
That's very true. Also, this answers to a question from Muhammad, which was, what do we do during the long shutdown? Which is, well, what has Zoltan said is happening right now. You need to imagine that we have right now inside CMS parts of the electronics, but also like, let's say, crystals and hardware parts that were designed in, I don't know, like 2002, 2005, and started running in 2010. So they are very old. And they have taken a huge amount of radiation. So this is why we are refurbishing mostly. So to, let's say, update it, use more modern technologies, and also to, let's say, change the parts that have ruined too much, because it cannot last forever with the radiation that it is receiving. I will answer just a couple of other questions while Derek gets ready to go down. I see, except for the questions on our career path, which maybe we can go through at the end, as Derek is now going down. I don't know what you think.
Yeah, during the time when.
Okay, and the dead times. Okay. Oh, that's okay. That's a quick one. Our scientific career started, I would say, with the PhD or maybe even master, because, for example, during my master, I was able to come here. I was lucky. There's like some internship that CERN makes available that are for master students. So I spent 6 months here working already on the system that took me in later on for the PhD, which is the colorimeter. We will talk about this. We'll describe this a bit later. So actually, it starts maybe younger than you would expect. I didn't think you could end up at CERN that early. I was like 23 something. And there's people that start here actually even younger.
Maybe longer time than you expected. My started more or less the same age
Yeah,
as yours,
fair
but
enough,
it
right?
was in a different millennium.
Don't say it with this like sad face. It makes you experience.
Oh yes, of course. Yes, of course.
We have Derek here that's ready to go down. Can you tell us what you're wearing and why?
Yeah. So Okay. So yes, what I'm wearing. So we have a lot of safety equipment here at CMS and CERN. So if you're giving a tour, which I am, you have to wear this vest that distinguishes me as a guide. But in addition to that, the safety equipment is a hard hat. Anytime you're underground, you must be wearing a hard hat. I have a personal dosimeter. So this measures my radiation dose. And we will see this is actually quite advanced because it's linked in the database to my personal body through my retinas. We'll come back to that later. But this measures my radiation dose while underground. And then I have safety boots on, or just closed-toe boots. They may be steel-toe. I can't quite remember. But again, while you're underground, it really is a workplace. You need to be wary of your surroundings and be well equipped. If somebody were to drop a tool from above, you don't want it to strike your head. So you should be wearing some sort of a helmet. Okay, so I think we're going to make our way down. But first we'll stop by the Peter Sharp room, which has parts of the detector in it. We could take some more questions while we're walking.
I can also show you a picture. Zoltan, can we show the picture of what CMS is so that you have an overview before you actually get to the Peter Sharp room? So, okay, what you see here is our detector. It's a cylinder because the interaction point is here in the very center, and particles can go basically everywhere around this point. So we need to capture them at all places. That's why it's basically closed. It's, well, not hermetic. We wish it would be. What do we have? So starting from the very center, you can see first light blue layer, which is the tracker, which basically is made so that it follows the track of particles without damaging them. So the particles survive, but we're able to say where they passed. So this gives us the direction of the particles and helps us understand, for example, the charge. Then we have the other blue part, and the yellow one, which is calorimeters. They are needed to measure energy. So basically, a particle passes through it and dies there. So it releases all its energy and we measure it. Finally, the only particles that survive are passed through the external side, which is the white bars within the red, which is the muon chambers. The muons are the only one that interacts so little that they don't release all their energy in the previous layers, and we measure them here. We also have the white part in the middle here, which is the solenoid or magnet that bends the particles so that, for example, we're able to measure its momenta, and also we're able to tell what charge they are. If there were no magnetic field, they would go straight and we would miss a lot of important information. I will stop bothering you. Oh, this is a picture of the, let's say, a slice of it. So you've got the tracker that doesn't stop the particles, but tells you where they passed. Then we've got the two calorimeters where they die. And finally, just the muons survive and hit the outside chambers. So this helps us to, for example, detect electrons in the first part and photons. And we've got in the hadron calorimeters, the hadronic particles, and finally muons. I will let now Derek show you the actual parts of the detector.
Thanks, Giulia. So we're in another part of the above ground facility. This is called the Peter Sharp room, named after Peter Sharp. But we have various pieces of CMS all around this room. And so we're going to go around, and you can imagine that you're a particle that was produced at the center of the collision. And this is your journey, outwards through the CMS detector. So the innermost part of the detector, the first thing the particles go through, or we would go through, is the pixel detectors. So up close, they look like this, which is just a gray sheet of silicon. But they are actually, if we look on this screen, very tiny pixels. So these are actually not unlike the pixels in your phone camera, but every single one of these tiny rectangles is a particle detector on its own. When a charged particle goes through this pixel, it disturbs the electrons in that pixel. And then we would see that as just a little pulse. And that's really all we want to see, is just, did it hit here or did it hit here? And then you can imagine in 3 dimensions, if you have a
couple layers of these. You have a hit, a hit, a hit, and then you draw a line through them. And that's how we get what we call a track. That's our very first, you could say, very first part of the reconstruction of the charged particles. If you have a neutral particle, they do not interact with the pixels. So that has some interesting implications for their identification. Also, pixels are part of the tracker subsystem. So often we'll just say tracker, but tracker is made up of two things, pixels and these silicon strips. So the pixels are 3 layers. They're closest to the collision point, and they're the most radiation damaged detector by far. They have the highest flux of radiation through them, but they are crucial for reconstructing these tracks of the particles. If we look here, these are some examples of the silicon strips. So these are what is immediately right outside of the 3 layers of pixels. We then have 10 layers of silicon strips, and they're similar to the pixels. They're a bit cheaper to produce, and they are more radiation hard. I mean, they last a bit longer. They're also receiving slightly less radiation since they're a bit further away from the interaction point. However, it's the combination of these strips and the pixels together how we get these very high resolution tracks for the charged particles coming out of the primary vertex. So this image here shows you the trajectories of some of these particles. And so we actually have to, disentangle all of these different trajectories from one another. So it's not an easy task. There's some more technical details. When we cross the proton beams, there's usually about, this will be the high Lumi upgrade, I think. There's multiple collisions, actually, when we cross the proton beams. There's about 60 collisions right now per bunch crossing, and bunch crossing is just the bunch of protons when we cross them. They're like little handfuls of protons. And so we have to be able to disambiguate these 60 different collisions from one another, and that's largely in part due to the resolution of this pixel and also the strips. It's a very, very challenging technical, I'm missing my words, but it's very challenging. So
Hey,
right
Derek,
outside
can
of the
I
tracker.
ask you something? Wait,
Yeah,
I have
of
a
course.
question on the outer tracker here. So
Yeah.
I'll send that to you. They're asking what are the biggest challenges in large scale module production and integration, for example, for the outer tracker. So I'd say you can tell us something about, well, what's the challenges in the production and installation of this, which is, well, quite
Okay,
complex.
that is a good question, and I'm glad you picked my area. So I personally work on the pixels. The silicon strips, not so much. However, I think what I can say about the two is the hardest part or the largest challenge of this subsystem of CMS is just the sheer data output. So right now in the current CMS detector, we have about, it's somewhere between, it's on the order of 200 million pixels. The number in my mind is like 250 million, but it doesn't really matter. It's about 200 million. That's a lot of pixels. That's a lot of individual data channels, okay? So you have 250 million data channels you got to keep track of. But we also need to remember this is a physical experiment taking place in a 3D space. So how do you have enough wires in that close or that compact of a space to even read out 200 million or 250 million pixels? So this is an extreme challenge, is actually just the data readout. And it only gets worse, or I shouldn't say worse, it only becomes more challenging for this upgrade we're about to do to CMS, where we install even more pixels. We've had a long time to develop this next generation pixel detector for our upgrade in the next year. And we're going to go from about the 200 million mark, 200 million pixels. We're going to go up to about 1 billion, I believe, pixels. It's quite the increase. And again, when you increase the number of pixels, you're increasing the number of wires or the readout. So to get back to the question, the challenge is actually, you wouldn't expect this. You can design these very tiny pixel modules, and we contract companies to help us with that. But the biggest challenge, in my experience, is actually just the cables, and you wouldn't expect that. So my university, we're actually hand-making cables to read out the electrical signals from the pixels, and we're calling the cables E-links. You would normally use Ethernet for this case because you can buy it off the shelf and it's very high data transfer. But Ethernet does not fit in CMS for 200 million or a billion readout channels. So we have to make these cables by hand. It's quite an in-depth answer. That was a good question though. Yeah.
Thank you.
And I think, yeah, the takeaway is that all across CMS requires very unique solutions to things you normally wouldn't think about. Yeah, I'd like to move on though to the eCal now. So right outside of Tracker, you have the eCalorimeter, eCal, electromagnetic calorimeter, sorry. So eCal, its main job is to completely stop and measure the energy of electrons and photons. And you may remember that's what a calorimeter is. That is a device that measures energy. So Tracker did not actually stop any particles. It doesn't want to, in fact, it wants to let them pass through. eCal, however, would like to stop photons and electrons. And we have these very expensive but very high-tech crystals that are actually lead tungstate. So it's a very interesting thought, but a majority of this material by mass is actually metal, yet it's optically clear. It looks just like glass. And so when an electron or a photon smashes into it and deposits all of its energy, here's an example of the crystal actually. When an electron or a photon smashes into this crystal, it deposits all of its energy and it gets converted into light. And then we measure that light with this light detector here. And then that gives us, by the quantity of light you measure, that gives you the energy deposited in this eCal. And Giulia could actually, if there's any questions about this later or now, she could actually answer them more than I could, because I don't work on eCal.
Thanks. If I see any, I will do answer, but feel free to go on.
Okay.
You explained it very nicely. Thank you very much.
Thanks. Let's look at this picture though. There's about 76,000, I believe, or 80,000 according to this number here. Nearly 80,000 of these crystals inside CMS. And if I'm not mistaken, this was one of the most expensive, if not the most expensive part of CMS, was this eCal. And it's very, very performant though. I would argue it was worth the cost. Okay, so right outside of eCal, we have HCal. Has a similar job in the fact that it wants to stop and measure the energy of a particular type of particle. In this case, it's the hadrons. So HCal stands for Hadron Calorimeter, and hadrons are particles that are made of quarks. These would be, examples of these would be even like a proton or a neutron. So you could have charged hadrons coming out of your collision. You could have neutral hadrons coming out of your collision. But in either case, they should be completely stopped by HCal, and we could measure their total energy. We're going to speed up here. But right outside HCal, we have the solenoid. And here's a chunk of it. In the middle of this metal bar is the actual part that carries the current. This is a superconducting material, niobium titanium, and this material at the middle needs to be at minus 270 degrees Celsius in order to be superconducting. And we want it to be superconducting so that we can pass an enormous amount of current through it and get a very strong magnetic field. So the solenoid was the heaviest part of CMS. And the crane we brought in to lower it, I was told a story that the cables even started to snap, one of them, by the time it was near the bottom of the shaft. So it's a very, very heavy solenoid. but it gives us this very strong magnetic field. We will kind of rush through these ones, but they can all be categorized as they're muon systems. So anything that wasn't stopped by ECal would be a hadron or a muon. And then anything that's not stopped by HCal should definitely be a muon. It's not always 100% the case, but it's usually the case. And so we have many different muon systems that are going to get the tracks and more information about these muons that make it through the solenoid even. And so I won't say much also because I don't work on the muon systems. Most of them operate under a principle that you have a noble gas inside of this material, and the muons being a charged particle, they will knock the electrons off of that gas. And then again, you're just detecting this excess of charge in some of these locations in the detector. And that's your hit for the muon. So
while you go downstairs, I will
yes,
like take the time to answer a question specifically on muon
perfect.
that was asked, which is how do we distinguish between the muons that are actually coming from a collision and the ones that are coming from outside? So that are, for example, I don't know, cosmic muons. And actually, Zoltan is the expert on muons, but he was just telling me that with the trigger, the muon trigger, we have systems that are able to detect whether a muon has started from the center of the collision. So if it's passing through, let's say, the first, second, third, and fourth muon chambers at the correct time for the muon to be not coming from the outside, but from the inside. So let's say the easy idea of the algorithm is that it passed first in the innermost chamber, then in the next one, then in the next one, then for sure it's coming from the inside and not the outside. So let's say this is a bit actually what happens for all the detectors in different flavors and different ways.
Right. Okay.
You guys want to go downstairs or?
Yes, I'll just point to this real quick, less than a minute.
Oh,
So
we're
all those
showing it.
ideas. Oh, sorry.
Oh, no worries.
So
It's good.
this picture conveys just those ideas where you have your tracks here from the center of the detector, you have your collision. And then if you see a curved track, we didn't quite talk about this, but if it's curved, it's a charged particle because a moving charged particle curves in a magnetic field. So if you see a curved track and then a hit in the ECal, you should have an electron. If you don't see tracks but a hit in the ECal, you should have a photon because they're neutral. And then it's the same idea for the hadrons. If there's a curved track and then a hit in HCal, that should be a charged hadron. No tracks and then a hit in HCal would be your neutral hadrons. And then anything that makes it all the way and makes hits out here should be your muon. And with that, we will go underground. We would like to show going through the door with the dosimeter, but in the time, absolutely take some questions and talk.
Okay, I will pick up a couple of questions. So the last one I see is on the conversion of the particles into light. Let's say, how do we see them, for example, in the scintillating crystals? I will speak for eco because I know it better. The scintillation light comes from a process that's called scintillation. So basically, you need to imagine that the crystal can have let's say, a non-excited state. And when a particle hits it, there is excitation. The material then goes back to its, let's say, baseline state by emitting photons, which are the fluorescence light, the actually scintillation light that we capture inside the crystal. So whenever a particle hits, this process is triggered and we can see light when where the particle actually passed.
Exactly, pair production, Compton.
Yeah, exactly. There's a set of exactly a set of process that triggers this. I would say this is answered, and you guys are at the door.
Oh yes, we're here.
Okay, you can go through. I mean, you can explain how to go through.
So I'll be quick, but I mentioned in the control room, this dosimeter is actually linked to my body. So when you're assigned your dosimeter, they scan your retinas at the exact same time they hand you it. And so it has my name. However, in the database, it's also linked to some sort of map or image of my retinas. So what's going to happen is I'm going to scan this. The door will open. I'll step in. It'll shut with me in there. It'll scan my retinas with this little picture box. And then if it matches, if this dosimeter matches the retinas on file for me, it'll open the next door, and then I can go into the area where there's the elevator to go down. So let's try this. And it may kick me out if it malfunctions. However, okay. So it took a picture of my eyes. And I think my glasses messed it up. So I must
you're
try
hearing
again.
the machine saying sorry. Well, in the meanwhile,
Oh, really? You can hear it?
Yeah, we can. I mean, I could.
Indeed, the machine didn't feel any sorry.
Yeah,
Take some more
exactly.
questions.
Yes, so I have, let's say, an answer to one of the most recent questions that we got, which is, does recent AI advancement allow us to distinguish and label data easier, and how, well, when was it implemented? And we have another one that's similar about AI helping us to filter events. Both actually, the answer to both questions is, yeah, AI actually helps us. So we have several machine learning algorithms that are running mostly, though I think we are developing them for the high luminosity phase. We're working on several different aspects. One of the problems of machine learning is that we needed to be fast enough to cope with our rates that are very, very high. So we have a collision every 25 nanoseconds. So we, for example, we're trying, I know like some of my friends are working on implementing machine learning on FPGAs, which makes it much faster. FPGAs are some sort of a, let's say, hybrid between doing things hardware and software. So they're much faster than, for example, let's say coding a neural network in Python, as maybe many of you have also tried. So yeah, we are working on using AI more to help us with those discrimination. You're in the elevator, so probably we're gonna lose the connection with Derek. Oh yeah, we already lost it, but we have some fun facts about this elevator, so I will answer this. The elevator is actually the safest spot that we have in CMS. So they always tell you not to take elevators when there is, I don't know, a fire or an emergency. This place is the exact opposite. So you need to take the elevator. We are going downstairs of about 100 meters. So it would be too slow to walk back up if there's a problem. Plus, the elevator has a pressure that's controlled so that it's always, the pressure is always a bit higher inside than in the cavern. So for example, if there's the release of some gas, for example, from, I don't know, the immune system, have some poisonous gases, if this leaks out, this will not get into the elevator. So just by running to the elevator and staying there, you'll be able to breathe fresh air. Of course, we do have safety masks. You'll probably see them. Derek will show us one probably soon. But this is one of the safety measures that we have implemented. I'll give it back to Derek because I see he is under like the hole.
Yeah. So we rode the elevator down, and we did lose our connection, unfortunately, for a moment, but we're back. So right through, I don't know how visible it is to you guys, but right through that cement door, it's labeled UXC55. That stands for the experimental cavern. And just on the other side is the CMS detector. All of that thick concrete is actually what keeps us safe and absorbs all of the radiation coming out of the collision. And it allows us to be so close to it, yet be completely safe. We can try to look up to see just how deep we are. So we are 100 meters underground. This is a shaft. I'm actually unfamiliar with what this shaft specifically is for.
Oh, it's the one where
Okay.
I'm pretty sure this is the shaft where they dropped CMS down. Is that right, Zoltan, or is it the second one? Oh, that's a smaller one. Okay. The other one's
because
probably
exactly
at this
at the
line.
top.
Right.
Okay.
This is not the shaft that CMS was lowered down, but it's right beside it. So our elevators here. We're going to go into the counting room now. It's our nickname for it, but this is the room that has a lot of the hardware and the readout electronics that are required to keep CMS operational.
This
can't
is
fit.
also like, we will take the chance to
Mhm.
answer a couple of the questions that are, someone asked, what happens to the data after we have collected them? I don't find again the answer, the question exactly, but this was the point. So now Derek will show us exactly what happens, like how data are collected, so how the trigger works, and then where the data go.
So trigger, I mentioned upstairs. Trigger is responsible for filtering out what events we want to keep and which we want to discard. We would keep all the collision events if we could, but it would amount to, I think, like petabytes per second of data readout, and that's just not physically possible. So trigger is very crucial for selecting events that have, for example, you could say, I only want to record events with 2 muons, and then trigger will watch for events with 2 muons, and when that occurs, it will read it out and store it to a hard drive, but otherwise it will just clear the memory.
This is what we did for the Higgs boson, for example, because we know that it decays, for example, to 4 muons. So we were super interested in all the events that had featured 4 muons at the same time. Not only, though. Also, there's, let's say, other interesting signatures.
Yeah, and then also what I want to show you is some of the readout electronics. So for the pixels that I was talking about, these are the pixel feds. And what I can point to here is these cables that are like a cyan or a light blue. They're actually fiber optic cables, and they're coming right from the CMS detector. So because we have such a strong magnetic field inside CMS, we actually don't want to keep or we would like to convert our electrical signals to optical as quickly as we can. Not necessarily for speed, but just because it's easier to transfer this light information all the way outside of CMS. And then it's that type of signal, fiber optic, is unaffected by the magnetic field. So all of these feds are crucial for the data readout of the pixels. They receive the collision information over these fiber optic cables, and then they actually do some stuff with it and transmit that data off to the next part of the readout chain. But it's a massive operation for each subsystem. I believe every subsystem probably has some sort of electronics in this room. I'm only most familiar with these ones because I work with the pixels. So an example of what it's like to be on shift also is one of these went bad and we didn't know which one. So we had to just come down here on the fly and look for which one had the lights off. And when we found it, we pulled it out, put a new one in, programmed it. It took about a couple hours to tinker with it, but we got it operational again, and then the experiment could continue. But that's kind of an example of what it's like to work on this experiment. You know, you never know what's going to happen, and you have to be ready to fix things as quickly as you can, because the entire detector depends on each subsystem to do its job. If you want to answer some questions, we'll walk just a bit further.
Oh no, I was not talking.
Hello?
So Zoltan
Yeah, sorry.
was giving me, yeah, no, thank you. Zoltan was giving me the camera because someone asked if we like ducks. We do like ducks a lot. So you're seeing that I have one in my hands. Reason why we like it is that Derek was talking about data acquisition. Data acquisition is in short DAQ, but if you're not spelling it, you read it DAC. And that's why specifically in the DAC part, we've got so many rubber ducks. And yes, this is, I don't know if this is just CMS or this is everyone. Maybe it's our thing. I don't know. I like to think it that way. So that was the DAQ question. And I have a question on the solenoid. I don't know, Derek, if that's a good time, you tell me.
Yeah, we can answer it.
Okay. So someone's asking, Kaveri is asking, how are the minus 200 degrees maintained? Yes, okay, that's actually correct. So we're just, the solenoid, I think, is just 1 or 2 degrees higher temperature than the outer space. So we are creating really cold places here. The LHC vacuum as well is that cold, and the rest of the systems of CMS are kept, let's say, at controlled temperature, but much higher. So we're talking about 0 or 10 or room temperature, so 20 degrees. So we do cool things down in general, both in CMS and in the LHC with, for example, liquid helium and this kind of gases that are not gases anymore when they're that cold. So this is one of the, let's say, the strategies that we have to keep the cold. And this is one of the gases, for example, that could be, or liquids that become gases that could spill out of our detector if we had any problem. That's what I was talking about before. So I would say that was a good question. I hope that's answered. And we can answer another one, which is, if in order to study all the different trajectories in the detectors and so on, we need to consider particles as classical or wave function. I think we for sure need to take into account that they're moving at relativistic speed, like we're in relativistic regime, but we consider most of them as classical. There are some processes that like require to take into account their quantistic behavior. It's not really two separate things. We look at them the way we need to for each specific task that we have. I think I'm answering, like, this is the answer, right? Both. So the answer is both. Yeah.
Yep.
Okay, that's done. We like ducks. Yes, that's done. I think you can go on. You were about to go further, or?
I think he has some show to show.
We're not going to go further. We're at the end of
you're in the corridor. Yes.
Yeah.
Okay.
Correct. Yes. But we're at the end of this is all the further we can go at the time. So
we want to see the
beam is
magnetic
on,
field.
yes. Since the beam is on, we cannot enter, but this is the door where you would cross and then go into the experimental cavern. So if the beam was off, another time, we would be able to go in and see the detector. It is not safe at the moment.
Here we are showing also, next to your picture, Derek, we're showing the map of where we are. So Zoltan was moving the cursor. You see we're at this corner here. So we were in the service cavern before, which is down here, and we cannot enter the experimental cavern.
Yes, the beam is currently on.
Yeah, the beam's on, so very much don't go in there.
Yes.
There is a fun fact about this. You see that there's a lot of corridors that have sharp turns. Someone explained to me that this is due to the fact that radiation does not pass corners, so it goes straight. So there is, let's say, concrete corners everywhere so that radiation doesn't pass. This is not really needed in the case of CMS, but as we are underneath the, let's say, regulation for nuclear power plants, we had to build the structure in this way. So we're safe because the entire detector is shielded. But well, this is a fun aspect that shows you how also the, let's say, regulation and political aspect.
Actually, this chicane here is really for purpose.
Because
the
this
radiation right
in front.
Exactly, right in front of the detector. In the tunnel, the radiation might be really high. Actually, this really is what you said, that radiation doesn't go
cross corners
straight. Exactly, it doesn't like the corners. So that's why actually all over here we have, as Giulia said,
Derek, you're close to.
Yep.
You're close also to the. Oh, you go.
We are here at the end of the walk, basically.
Yeah, we're not able to go further. I see behind you an alarm. We were talking about this before. I see it on your left, which is your right.
But you do see me, no?
Oh,
yeah.
This is the.
Okay. So although we cannot.
Yeah, exactly. Left or right. That's hard. That's relative.
Well, although we can't go into the experimental cavern, we are right beside it. And inside the experimental cavern, there is a very strong magnetic field from the solenoid. At the center of CMS, it's 3.8 Tesla. And that's so strong that even this far away, there's still quite a strong influence of the magnetic field. So if you have anything that is magnetic, it would be attracted to and align itself with the magnetic field of CMS from here. And so it's very fun to play with this magnetic field. It's also probably one of the only places on Earth that you would experience something like this. And I even brought, just to show you a bit more, the field permeates everywhere. It's all throughout this room. So I smuggled a lot of these paper clips down, and none of them are connected. However, if I just drop some, and sometimes they take a moment to adjust, but they should, all on their own, kind of dance and align themselves with the field.
So in the middle of the detector, we have 3.8 Tesla magnetic field. That's about 100,000 times stronger than that of the Earth's magnetic field. This is almost entirely encapsulated inside the detector. You saw those red stuff on Giulia's picture just a couple of minutes ago. Very tiny amount of this magnetic field escapes. Also, the 7.2 meters of more iron than concrete wall just behind the rack also stops a little bit or absorbs a little bit. What you see here is really a tiny little amount that even escapes even the concrete wall. That has no effect on the human beings. By the way, the MRI machines operate at somewhere around 3 Tesla. So the human body can absolutely withstand it. We don't feel any problems with that.
But it needs, well, we need to be very careful. For example, you can't just like bring a hammer downstairs,
Right.
because the head of it, it's going to be, let's say, dragged closer to our detector. So we have to use specific, let's say, tools.
Exactly. When we have opportunity to go in with the virtual visits in the cavern, if there is no beam we can go in, we used to take another very sophisticated magnetic field indicator. That's an M19 spanner. We tether it to the wrist of the guide. Well, it won't fly through the room. Indeed, it's too heavy to fly. It would fall down. But anyway, it is always good to have a safety tether.
And it's fun also that you can see it when we go downstairs with the field on. The camera, if you get too close, doesn't transmit the image well anymore. It really gets all blurry.
Exactly. The focus puller gets a little bit crazy, so things get a little bit blurred. And if you get too close, even the G sensor in your phone gets affected by the field, so it might flip the image. That's really funny.
You're also seeing like one of the favorite physicists' activities in a magnetic field, which is playing. We are actually very simple people. We have fun with those beautiful phenomena that we see here.
I think this is the biggest threat with the magnetic field, that
we
lose the exactly. we lose the guide, and therefore we slip out of the time.
Yeah, that's fair enough. Maybe
many hours of work have been lost down here.
Oh, we have a question on, I think still in the magnetic field, which is from Cavalry, which is if the continuous exposure has any effect on the human body. Well, this question works for exposure to radiation and to the magnetic field. To the magnetic field, I would say absolutely not.
Absolutely not.
So it has absolutely not effect.
Not at this level. Of course, beyond 10 Tesla, we don't have 10 Tesla anywhere. Even in the dipole magnets of the LHC, we have something like 9 point something, but that's a very small and very encapsulated place. You cannot go there. Beyond 10 Tesla, you might have some neurological things, but definitely not at that level.
No. For the radiations, well, we pay a lot of attention never to get close to the areas where there is still radiation. So that could be CMS while the beam is on, but also CMS immediately after the beam has been switched off, because the materials can get activated due to the presence of the radiation. So we need to wait. There is a limit of exposure in the unit of measure of, let's say, the dose that you can get, which is the sievert, that we are always below. We use the dosimeter exactly for that. So you're able, let's say, to read out your dosimeter. You can do it as soon as you want, so that you check that you haven't gotten a dose that's dangerous.
Let me make a remark here.
Yeah, sure.
Our colleagues are not guinea pigs. We have those meters also on the walls, and we can read them out remotely. We don't need to send in anyone to know what the radiation level is. And we are extremely strict on this.
Yeah.
Indeed, we have quite a few safety mechanisms inbuilt. You saw just a minute ago, you saw that yellow door or even the red door behind Derek this time. If we would break through, I won't tell you how to break through. You would figure it out if you would stand in front of. But if you would break through, you would immediately shut down the 27 kilometers ring. You won't have a choice or a chance to get in front of the beam. No. That's one of the basics.
We also have a huge red button here that we can press in case of emergencies. It's the kind of button that screams for being pressed, but definitely not something you should do.
Well, you should.
I mean,
do
you
it
should do it if
you
in case. Yeah.
Exactly.
Exactly.
Not for joke,
not for fun. Not for fun. Derek's to show us the.
I'm here with yeah, you'd mentioned it, so I thought I'd show. This is the self-rescue mask. So some areas underground, not the one that we're in, require you to carry this mask with you at all times, and it's actually stored in this metal container. So for convenience, this is all it is, and it's hanging off your hip. And in the event of a gas leak or something that would push all the oxygen out of the air, even like a fire, if you're in one of these confined spaces, you're trained to be able to put this on in, I think, like 30 seconds or so, but very quickly.
Yep.
And then plug your nose and you breathe in and out of this tube, and this can deliver oxygen to you for up to 30 minutes to get to safety or wherever else you need to be. And yeah, so it's another safety device. I've not heard of any stories of people needing to use it, but we are trained to use it. And
really,
I used the real one. I was the trainer, indeed. I had to try it.
And so inside that room
really
is
this is an oxygen regenerator. It regenerates the oxygen from your exhaled carbon dioxide through a chemical process.
Right.
You don't need to have any atmospheric oxygen around.
Wow. That's like there is technology and fun stuff, interesting physics stuff, literally everywhere here.
Oh yeah.
I have okay, if you don't want to say anything else, Derek, I have another question on the magnets, as we were talking about this earlier, which is if our magnets, LHC magnets, are the strongest on Earth. As far as I know, the superconducting solenoid of CMS is the strongest superconducting solenoid of the Earth, but that's quite specific. The magnets of the LHC are extremely more
they are somewhere around 9 Tesla.
Yeah, exactly.
And there are some magnet labs where they can go up to several tens of Teslas.
Yeah, exactly.
The volume, however, is much smaller. So this is the biggest superconductive magnet with this volume.
Because the bigger it's called the yoke of the magnet. So the biggest the size of the solenoid, the more expensive the solenoid it is.
And technically challenging.
And technically
we have a 6-meter bore.
Yeah, that's huge. A person
once we joked with we had visitors from an MRI company, and we told them that your bore is somewhere around 70 centimeters where the patient goes through. We have 6 meters. We could bring in an African elephant.
Jesus, that's true. That's fun. I have a lot of interesting questions to answer. So I don't know, Derek, if I'll go on with this. I'll start from the last that we have and then go back. So they are asking us, how does CMS contribute to the search for particles beyond a star model? So supersymmetry or extra dimensions. So as I told you guys, CMS is a general purpose detector, which means that we're able to see all kinds of particles. So we're able to detect electrons, photons, protons, and so on. And that helps us because we're able to have an overview of the physics that's as general as possible. So basically what happens is that theorists, for example, people that work on supersymmetry, tell us, for example, if this supersymmetric particle exists, I expect it to decay after it's been produced in, let's say, I don't know, 3 muons and electrons with this energy and this characteristic. So what we do after that is that usually PhD students start analyzing the data that have been collected and try to look for an event that has the specific characteristics that we were told. This app, well, actually, we search for a lot of events, so we need the large statistics. This is exactly what happened with the supersymmetry particles. So we've searched for many of them, and so far we haven't had any luck. I will take a minute to talk about another aspect of searching for new particles that we have been exploring now, and it's also making large use of AI, which is the search of particles in a, let's say, agnostic way. So basically what we want to do is, what if the theorists haven't come up yet with the theory of a new particle? So supersymmetry doesn't seem to be working. We haven't found it yet. Can we, I don't know, look for something that's anomalous, but we don't really know what's the theory behind it? So that's what we're trying to do. For example, Derek told you about the trigger, which selects events based on what the theorists tell us to look for. Well, we're trying to overcome this limitation. So we're setting in place a system that's called the scouting, which is able to read all the data that we're collecting. So without, let's say, the trigger filtering them. We read data at every collision, so at 25 nanoseconds. And you might ask, why didn't we do that from the beginning? Because those data are very big. So first we needed the technology to do it. And just now this is appearing. And also we are collecting data with lower quality. So let's say it's like a picture that's less in focus, less pixels, but at least we can take more pictures. Hi guys. So I would say this answer is done. Then we have a set of questions on our projects or the projects of different, let's say, profiles at CERN. So I'll pick one from Roboter that's asked if we know for some career paths for like electrical and mechanical engineers at CERN. So there are actually a lot of engineers here, might even be more than physicists. Electrical and mechanical engineers are fundamental, especially probably, well, when the CMS was built and right now that we are working on the upgrades. So we are basically redesigning parts of our detectors and a lot of the electronics. The electronics in CMS needs to be radiation hard, just to say one, which is not standard outside CERN. So it's not, let's say, you just buy something that's radiation hard. Usually, of course, there is application outside CERN, but not as frequent. So this is one of the main tasks right now of our engineers, I would say. And another thing we can answer now is what are our paths? So what are we doing in our PhDs? Because someone was interested on our, let's say, career path.
Mm-hmm.
I can tell you that I'm working on a, let's say, two-sided project. So on one side, I'm working on the upgrade of the ECA, so the electromagnetic calorimeter, which means I'm designing the software to acquire data when we will have the upgraded electronics. So this means doing, I don't know, tests and code a lot. But I'm also working on an analysis of data that were collected in round 2, which was 2016, 2018. So actually, I'm doing a search for physics beyond the standard model in some sort of an agnostic way. So trying not to be too biased from the theory behind. So you can actually see aspects during your PhD that are quite different, like you get the chance to explore. I don't know if you're like in the same situation more or less.
Yeah, I mean, so before I moved here, I was doing some work with the upgrade of the pixels, testing of the new modules. Where I'm at currently, I'm doing a lot of just my analysis from here, and I'm also looking for physics beyond the standard model.
Oh, nice.
Yeah, not in an agnostic way.
Well, I'm doing EFTs, so
okay.
it's
Yeah. So
Yeah,
we're looking
hybrid.
for the technical term is compressed supersymmetry. So these particles that may exist, but they would have very tiny mass difference. So we think in terms of these particles decaying, what they decay to. And if you have this invisible particle and it decays to another invisible particle, it could emit a very low momentum particle. So we're looking for these low momentum electrons in CMS that would hopefully verify that these supersymmetric particles exist. So we're working on this analysis.
Yeah.
I hope to, in my career path, hope to finish this PhD and also get rehired as a postdoc and stay here. Continue the research, continue the work. But it's just it's like an electric place to be and to live, and
Yeah.
you don't get rich. I may never have a sports car, but I live a very meaningful
Well,
life.
we're
and,
still in Switzerland.
That's true.
There's another
That's why we
question
are
that's
not rich.
yeah. That's another question that's related, which is how many different types of jobs that there are within the detector. I think the answer is like infinite. There is really a lot of opportunities. Just thinking about, I don't know, my friends, so other physics PhD students, many people actually do PhDs on topics that are far more on the engineering side, but there is also a lot of opportunities on any sense. So we've got a lot of engineers that come here with internships. I'm talking about the students. Of course, there is also career paths beyond the PhD. So you can go on and work still here. We've got a lot of effort also on the outreach side of science, which I think is a pretty exciting part of CERN. So if you were to come here and book a visit, you could see the detector, like see a meter from you. I think this is actually quite awesome of CERN that you get the chance to explore and see with your own eyes something that's just cutting edge technologies and everything. So there's really so many different kind of jobs. Also like pure software things. There's a lot of machine learning. There's a lot of firmware, and
I think
literally
by now a majority of my friends here are not physicists. I thought when I moved here it would be all physicists, but it's actually a lot more engineers and also people that do more outreach stuff, some fundraising, some I would say the jobs that are just as crucial to keeping CERN and CMS going. But you know, the physicists.
One of the nice things is that like we all sign the papers of CMS, so this really means how much each contribution is valued, because as you can see, this experiment is huge. So you clearly understand that you need literally every contribution, from the guy that like laid the wires correctly, and we're talking about hundreds of wires, so it's super complicated, to the guy that did the most top level analysis, never saw a wire himself. So we literally need all the profiles. I think it's very varied, the landscape here. What advice would you give to young people who aspire to become a physicist? Then we also want to know it from you, Zoltan, from a more experienced perspective.
Oh my God.
My advice.
Very important to keep your interest in new things. You will see if you get here that this is the place where you can be creative. Actually, this is what I feel during the past decades. That I can be unlimitedly creative here. And this is something that is very fascinating being here. Apart from the physics topics that you both mentioned, I wish I would participate even. So these are extremely interesting being here. So for the new guys, but you don't need to be a physicist. This is what you just told. So in order to get here, first of all, you don't need to be born here.
Oh, absolutely.
The second is that you don't need to be a physicist to get here. All the engineers are welcome. We need quite a lot of computing specialists, electronic engineering, but also we have mechanical engineering needs
Yep.
actually non-standard mechanical engineering,
Definitely.
together with all the state-of-the-art technologies like the simulations of how the mechanical pieces withstand the different loads, but also even the civil engineering is needed here. So you might imagine that, as you just said, the full spectrum of people are welcome. This is one of the best places in the.
Yeah, it's also true. You mentioned like the how international CERN is. So there's several countries that are called member states, so directly finance CERN, and for those for people belonging to those country, there might be some more opportunities, but I actually have seen people coming from basically most of the states. Actually, the US is one of the most present, and you're not a member state.
Yeah.
Also, you don't need to be, I don't know how it works in your countries, but you don't need to be from a, I don't know, insanely rated university to manage to get here. There is a big culture of learning on the spot, also because it's very hard that you've actually already worked on something that we're doing here. For example, I see it as a PhD student, until you get there on the, let's say, hardware software side, you have not probably worked on that during uni. Absolutely. Analysis is also different from, let's say, quantum mechanics classes. So it's really, you start from scratch here and you develop as a physicist and not only as a physicist. So
and also, I would like to emphasize what you just said, the multicultural environment. Even at this moment in this control room, as I look around, we have 3, 4, 5 different languages. Actually,
at least.
At least. This is absolutely cool.
Yeah. No, that's really great. So you also grow on a, let's say, human side. I have another question for you guys, which is, I think that came on Instagram before. What is the most difficult thing that you have ever done? I think I do have one, but it's not
related to physics, no? So,
well, mine is related to, I don't know, like the hardest part of the way. We have 10 minutes. Okay. The hardest part of the way for me was the beginning of the bachelor. So I did a high school that was quite more related to humanities. So when I switched to physics, the beginning of my bachelor degree was very, very hard. Also, it was very hard to maintain the motivation. I think my uni friends saved me. So we helped each other studying and we all got through it. But yeah, this was my hardest part, let's say. It was not at CERN, I'd say.
I think it's similar. During my bachelor's, there was a moment where I had to, I did not go into my undergrad as a physics major. So I had to relearn a lot of math that I told myself I wouldn't need in the future. So I kind of did it to myself. But I think it says something overall. If you want to succeed in physics and really like kind of pursue this career path, you need to get comfortable with teaching yourself things, new things. I've had to do that actually every single day. You don't know something and you cannot always rely on somebody else to teach you. Absolutely ask people that do know things. They could explain something to you. I've learned just as much from other people. But it's almost like a seesaw. You have to learn from other people, but you also have to teach yourself. And it is a tough thing, I think, to know you don't know something and be humble about it and work it, actually learning it, whatever it takes. So
I will now pick a couple of more technical questions. So one is if we differentiate between charged and non-charged particles. We do that mainly of.
Let me just
Thanks. Yes. We do that thanks to the bending of the particles due to the magnetic field of the superconducting solenoid. So for example, you see here this red thing is an electron. If it were to be a positron, it would be turning the other side. So that's one of the reasons why we need this magnet. Then we have another technical question, which is whether if we had, let's say, the same configuration of detectors and so on, with the same proton beam but with a higher energy, would it be easier to detect more particles? Well, actually, this is a trade-off. Like, we can do that. So in our everyday life, in our everyday life, the let's say we call it luminosity, not brilliance, but still very good, let's say, guess. The luminosity can increase. For example, when we start running, it's at its peak, then the pack of protons, so the beam deteriorates and it goes a bit lower. We love having more particles colliding, but it makes also our life a bit harder because we need to first sustain a higher rate of data coming through. And second, we need afterwards, when the data is collected, to be better at discriminating what's good and bad in there. So it's some sort of a trade-off.
Also that true that the detector is designed for the maximum energy of the accelerator. Usually the limiting factor is the calorimeter.
Yeah. We become
we
black.
have to fit in the calorimeter
and
the particle avalanches. So if we would make a much bigger accelerator, then probably the calorimeters would need to be bigger. Therefore, the detector will become a little bit bigger. This is always working in hand. So
yeah, that's very true. We have a couple of other, well, quick questions. So if it's possible to conduct research abroad, absolutely yes. Like,
yes, we are doing.
That's how I started. So in the US at my university, I was working for CMS for probably 2 or 3 years before I actually moved here. And I was an author on CMS without ever having been here in person.
Like, you're a schooler.
Well, yeah. So
yeah, it's absolutely normal though. Like the amount of people working on CMS, if you consider all the people that are not here in person, is really incredibly large.
It's at least 90%.
Yeah.
We are over 5,000
in
the CMS collaboration, and I don't think that we are more than 500 here, even less.
Yeah, exactly. Then we have another question about what do we like most about your job, our jobs. What about you?
There's a lot of things I like about my job. And there's a few things that are tough about my job. What I like the most, I think, is that I have this liberty to keep learning every day. And it's very funny. Sometimes, and I like engaging with the public because sometimes a simple little question will actually point out, oh, I actually didn't fully understand this one thing, and it's another opportunity to learn. But day in and day out, I'm learning and improving certain skills and learning more about particle physics in general. It's a very, just a rewarding thing to have a job where you're always doing something different day to day, within reason, and you're learning constantly. So I love that. Yeah,
that's fair enough. I think for me the answer would be this. And I also particularly like doing the, let's say, hardware and software side, where you have a problem, you have something in front of you, you make it work, and you actually see the practical result of things. I suffer a bit more from working the entire day in front of a screen. So being actually here and doing both analysis and hardware and upgrade helps me a lot get through both parts, because I know that both are useful. But if I were to only do maybe analysis, which is also a bit more of an individual work, that maybe would get a bit harder for me. So yeah, we got the sign that we need to finish. I just missed the single question. Can I answer it?
Yeah, sure. Go ahead.
So the last question I will answer, because it's the last one I got, is from someone that's studying applied physics and would like to ask what are the careers at CERN that follow this direction. This is actually the widest.
That's a very broad question.
Yeah, that's the widest spectrum. Like for applied physics, you have everything, not only inside the detector itself, which is what we talked about. So we're both working a bit on applied physics, but also on other aspects of the LHC. For example, there's a lot of other detectors, some that are not even mounted on the LHC, that study all sort of things. There's, for example, an experiment called CLOUD that study the way clouds are formed. So there actually the page of CERN where they advertise job position, or at least internship position, is, in my opinion, the best spot where you can have an idea of all the possible options that you can follow. But there's everything from software, machine learning, to electronics and hardware development. So
I have
it
friends
really,
that work on the beam.
yeah,
they
beam
do a laser
beam
thing.
department is a huge thing.
Yeah.
Like they make us, they make
Yeah.
everything for us.
Cryogenics.
Cryogenics is a big part.
It's any cutting edge area
Yeah.
of engineering. I would
There's
say.
also a lot of medical
Yeah.
physics because, for example, beam technologies are used also for hydrotherapy, which is used to cure cancer. But also the same crystals, similar crystals to the ones that we use inside CMS, are used for the PET scans. So for the detection of cancer particles and cancer cells. So there is a very, very, very wide range of opportunities, not only high energy physics related.
Yeah.
So
Exactly.
yeah, I don't know. I think we should say goodbye on this
I
note,
think that
right?
the time is up, but it was very, very interesting, very fascinating.
Yeah.
This visit.
Thank you very much for
Thank
the
you very much,
participation, guys.
Yeah.
It was
Thanks.
fun.
Have a nice day. Ciao,
Ciao,
ciao.
ciao.